So because this meeting is about resurgence and modularity, I have to talk about some part of it. So I'll talk about strings, which has modular properties today. So this work mainly will focus on the work which will appear soon in a week, which is done by Hichal Kim at Postec and Kai Wen Sun at Uppsala and Shin Wang at Kias. Right. So I mean, our group has been working on instantons and calculation of the instanton partition function for last 12 years, and we owe largely to Italian group for our initiation. I don't know whether you guys know about it, but I think ICTP school taught Hitchell uh, how to calculate omega deformed Nekrasov partition function, and then we learned that around 2010 or 11. Then we started to work on this subject, and I realized also we've been working on the various partition functions and the integral models and the surface defect, and you guys are largely working on 4D problems, and our interest overlap quite a bit. So hopefully this will be also a good starting point for conversation. So strings as a relativistic object has been quantized for free string case, and we got bosonic case critical dimension 26, and then supersymmetric case 10 dimensions. Now, of course, in real world, like a four-dimensional space-time, we have a vortex string. And if you turn the water, then there's a vortex string, and that's a stringy object. But we know its critical dimension is 4 because it's living in 4 dimensions. And also, if we have think about magnetic flux vortex in superconductor, again, it's a 3-dimensional object, 3 plus 1-dimensional object. So those are there, and but people have studied the motion of the say smoke rings or vortices. There's corresponding integral models. Is generalization of a particle on uniform magnetic field, string moving on uniform density. There's some Landau problem, and that has been integrable. Even though I guess the arcade may be applied to S3 cross the ADS3, where you have constant three-form flux, and then you have a vortex moving on it with, I would say, it's Magnus force, then it's integrable. Now, that's 3 plus 1. Now, 4 plus 1 dimensional case, also again, there are natural object, which is, so think about 5D superconformal field theory, which is made of the PQ string webs. And in which case, this results, again, even though people have calculated this object, the class of partition function, Kupakuma buffer invariant, and so on, very extensively, this is a rather mysterious theory in a way. So this is conformal. This 1, 1, 5 brane and 1 minus 1, 5 brane intersecting. Then you go to Coulomb phase. Then TCL has low energy effective Lagrangian, which is U1, n equal 1 supersymmetric U1 theories. So U1 Maxwell theory, supersymmetric theories. But TCL has 2 W bosons, which are mutually non-local. So one comes from fundamental string connecting these T5 branes, which of course give us weakly coupled region where we interpret as W bosons. And then you can have a S-dual Bourdonnais, which is T1 string connecting two NS5 branes, and those are instantons. And one of the excitement of instanton is the W boson with vector multiplet. So this is not electromagnetic duality in 4D sense. In 4D again, we have U1 theory, then we have electromagnetic duality, which means we have monopoles and then W bosons. But it's not magnetic object. Both of them are electric object. And they are mutually non-local. And if you do the Kuppako-Mappa invariant, then for this massive vector boson, there's two PPS objects.
Sorry, the risk of exposing my ignorance about diagrammatics. To which extent is this a statement about string and V-brane configuration?
Oh, so right. So this is a D5 brane, and this is NS5 brane, and then they merge into 115 branes. So code dimension. So this is like say 0, 1, 2, 3, 4, 6. And this is like 0, 1, 2, 3, 4, 5. And then this is a 5, 6-dimensional plane. And then common dimension is 0, 1, 2, 3, 4. So it's 5-dimensional physics living on it. So this is a very strange theory. So SU2 is, for example, 5 flavor. There are 27 W bosons for single U1 mass respect to multiplex. So that's what this red mystery is. But here, I want to talk about strings. So in this case, we can have monopole strings. Because in 5D, 4-dimension monopoles and electric charged objects are local objects. But in 5-dimension, magnetic discharged objects are like stringy objects. And this is the one where D3 brane wraps this XY plane. So the remaining direction is the magnetic object. So this object, of course, some people study the modularity, but transverse direction is 3-dimensional, so it has wall crossing phenomena. And this partition function is not exactly modular function, it's more modular functions and so on. And my colleague Sungjae Lee and Jeff, maybe when he was postdoc, they calculate the partition function of this subject. But today I will work on somewhat simpler, which is 5 plus 1 dimension. Superconfirmed field series and little string theories. And those theories are supposed to be UV completion of, say, higher dimensional quantum field theory without gravity. And for example, superconfirmed field theory, one can have only 2,0 supersymmetries, and that arise naturally from, say, M5 branes. And then on which fermions are chiral, that's why it's 2,0 from, and also field, instead of ordinary gauge field between, so if we have D branes, then we have fundamental string connecting D branes and generate the Yang-Mills theories. But for M5 branes, natural object connecting them is M2 brane stripes. And field theory living on M5 brane is some sort of two-form tensor field whose field strength is dual on the, is it Poincare duality? Oh. So 3-form is dual to itself, and it has 3 degrees of freedom, similar to 60 photons. Right, so because this field strength is self-dual, this two-form field is coupled to this M2 brane whose world volume is some line. So roughly there will be a line of M2 brane connecting two M5 branes, and they generate this current, antisymmetric tensor current, and they couple to each other. But usually this could be in this flux case. We know, for example, Goldstone boson can be, and then for this vortex generate coupling between this 3-form tensor field and the vortex lines. But here flux is self-dual, so source has to be self-dual. So we call it to be self-dual string, which means it's both electric and magnetic. whose field strength is equal to 1, so that there's no weak coupling limit of this series. Right. So this is self-adjusting. So those are objects we are interested in today. 1,0 case, when we reduce the supersymmetry, story becomes more interesting and very rich, but I don't think we have time today. And also, I haven't worked with much of that those theories. So these theories, when I multiply M5 branes, I can put them on top. There's a Coulomb parameter between them, tensor multiplies. So if you look at the multiples structures, then you have B mu, scalar, then fermions, which in terms of 1,0 tensor multiplet. Then you have 1,0 hypermultiplet, and there are A equals to 1 to 4, and the psi is again the same chirality as this 1,0 tensor multiplet. And T theory, people have been trying to write a Lagrangian, and it has been that successful because you are trying to write a Lagrangian on both electric and magnetic object. And in 4D theory, there's some attempt by Zen and many others, but not really successful in my opinion. And 60, again, there's no explicit Lagrangian which captures the non-abelian property of it, because there is no non-abelian gauge symmetry. So here, non-abelian gauge symmetries emerged when we compactify this theory on a circle. Then if we regard this circle as M circle, then M5 brane wrapping the circle becomes D4. So if we have multiple D4, then we have a 5D n equal to maximally supersymmetric Yang-Mills theory for N M5 branes. And then KK momentum becomes D0 brane, and D0 on D4 becomes instantons. So as Seiberg said almost quarter centuries ago, instantons in maximalized supersymmetric 5D Yang-Mills theory is KK momentum, which so that strong coupling limit of the Yang-Mills theory is where instanton gets lighter and lighter. KK momentum gets lighter, which means your theory compactifies to 60 conformal field theories. All right, so that's briefly review 60 conformal field theory. Any question? Right. So let's go to little string theories. Little string theory, there are two versions of it. Maybe it's better to study little string theory. So before that, 5D conformal field series, 2 conformal field series. There are 3 types of series: AR, BR, E6, 7, 8. They are all simply Lie groups or algebras. So there's naturally corresponding conformal field theory, but there's no Lie group, say. So, but thinking diagram sometimes captures the physics of these theories. Now, so we stack the M5 branes, and then transverse direction is 5-dimensional, non-compact. So that's why we have 5 scalar fields, which is non-compact. But instead, let's compactify one of the transverse directions, say this to be. So we are compactifying one of the directions. And then we regard that as M circle, then we end up with type 2A string theory. And 2-dimensional little string theory arises from the of course, there is a different way of getting from 2B theory using geometry, but from brain picture, very simple to get. 2,0 A-type series we just obtained from n ns5 rings, which means that we have M circle now. And then we have M5 rings. And previously, this was non-compact, but we compactified it. So let's say this is alpha 1, alpha 2, alpha 3, alpha 4. So we are giving elementary M2 brane, connecting M5 brane as a simple root. Then there's one last one, which is coming back. So we have alpha 0. So we have natural thinking diagrams. And each root represents this self-dual string. And also, if we wrap this theory on a circle, then we get a 5D Yang-Mills theory in this case, and this root self-dual string becomes W bosons. And similarly, if we wrap this theory on a circle, then we get 5D Yang-Mills theory with W bosons related to alpha 1, alpha 2, alpha 3, alpha 4. And also, there's one more W boson related to alpha 0, which is not there on multiple dipole branes. Right. So as I say, 2,0 conformal field theory comes with ADE type, and similarly, so this arises from 2B theory. We mode out the C2 by discrete subgroup over SU2 over AD type. Then from 2B theory side, then we get this conformal field theory. But one has to do a little more. One has to generalize this concept to Calabi-Yau, K3 surface with toric, and then you can add this one more node related to affine thinking, affine node, and then this theory now has some scale, and and the way we decouple the string gravity is we make GS go to 0 and LS scale fixed. So we fix the fundamental string tension scale, which is fixed, but string coupling to be very small, then gravity decouples, and you get a constant 6D theory, which is a little string theory. And as I said, there are again AD type. That's T type, and E6 affine E6, for example. So this affine thinking diagram captures 6D 2,0 little string theory. So you don't need to go to 5D to have a affine property because we have hidden M circle there. Now, so we'll be interested in the self-dual strings, which form a little string. So, so little string is the one where fundamental string, which means fundamental strings wrapping the M circle by ones, which means it's made of the self-dual string, A-type case, so fundamental string. Is made of the self-dual string plus alpha 1 plus alpha 2. Okay, and so if I just look at the charge of this theory is equal to 0 because that's what A-type is. So which means when I wrap this M circle with M2 brane, this charge of the two-form tensor field cancel each other. So it's charge neutral. That's what it means. So, And that's so middle string, which is fundamental string on M5 ring, is charge neutral. On the non-abelian tensor field, or it decouples. So naturally, there's a concept of global U1 symmetry. So there's the one form symmetry. It's conserved. And for AD type, in general, A type, we just add all the simple roots together, and then it becomes 0 because we go around the ones. But D and E type, we cannot have that simple sum. D type case, for example, 1, 1, 2, 2, 2, 1, 1, we have to add with a non-trivial coefficient, and this AI is called the marks. A0 equal to 1, and that fixes non-negative integer AI completely. And so, for example, that two-form tensor field is charged to be 0. Single little string is made of this fractional self-real string whose tension will be depending on Coulomb tensor parameters, but such that whole tension is independent of the local tension which self-real string can have. So, so this number, total component, is called the Cox's number. Okay, and the single little string in two-comma theory of AD type split into H number of bits, and the type will be each of type of the self-real string will be given in terms of these marks. So AR type is R plus 1, DR is 2R minus 2, E6 is 12, E7 is 18, E8 is 30. Those are the Coxton number, or Coxton number of the ADE type. And the marks and comarks are identical for simplest groups. Okay, so that's for two-comma reduced string theories. Now let's look at yeah, I haven't used anything, so it's non-touched affine diagram, and those are the, if you just think about 60 theory without compactifying anything, then only those theory appears in with 2,0 supersymmetry, and just affine nodes, no twist affine nodes. So those theory with twist affine node is not present as a 2,0 little string theory. You cannot decouple the gravity. So 1,1 little string theory in 2B setting, it just comes from A type. Again, NS5 brains plus one fundamental string. And fundamental strings. So physics on NS5 brains in 2B theory seems to be very complicated, but we cheat by using S dualities. And then it's n d5 branes, and then one d1 strings. Okay. Now on n d5 branes series, Yang-Mills theory, 60 super Yang-Mills theory. We know very well. So a mu and the phi 1 to 4 hypermultiplies. And the gauge field in 60 has 4 degrees of freedom. And D0 brane on D4 brane is instanton. Similarly, D1 string on D5 brane is instanton string. So we can write down 60 low energy effective Lagrangian. Not like a two-comma theory, we can write only abelian part of the theory, not non-abelian part of theory, because the source is a string, self-zero string. And this case, Lagrangian is just okay. And then, so roughly G Yang-Mills square this is the inverse Yang-Mills square, and the instanton string has a tension a pi square over G Yang-Mills square, which is just inversely GS LS square, which is D1 string tension. Okay, so we have Lagrangian. Low energy dynamics. So we know 60 1,1 supersymmetry Yang-Mills theory, of course, it's non-renormalizable and UV incomplete. But somehow, if you do the instanton physics right, instanton string physics right, it becomes UV complete reduced string theory. Now, because when we SQL to NS5 branes and fundamental string, only then we can take a limit where GS goes to 0 and LS scale fixed, which is the string limit. And then, because low energy physics doesn't care about the S duality, because low energy physics. So it will be invariant on the S duality, which means that only thing you have to do is change the parameters. So it's LS square, and the LS square then is fundamental string tension. So on NS5 branes in 2B string theory, low energy physics is given in terms of 61,1 Yang-Mills theory, and instanton string is fundamental string, and you identify coupling constant as one of LS square. Now, there's another way of getting it 1,1 Yang-Mills theory, start from M theory. And we think about M theory on C2 divided by AD. And then if we blow up the AD singularity, then we get a surface which you can wrap it with M2 branes. So we can get the 70 Yang-Mills theory. So this will generate the 70. AD type. And 70 Yang-Mills theory, you cannot decouple the gravity. So you have to include the 10D string theory or 11D Yang-Mills M theories. Now, instead, we compactify this theory further. And regard that as M circle, then we can take a GS goes to 0 and LS square fixed. But we can do the twisting on this theory. Because the 70 Yang-Mills theory, circle compactifying, then we can twist the Yang-Mills theory. And then we end up with 6D 1, theory of A, E, C, E, E, F, G. We can get all the non-simplest group. In addition, there is a fifth homotopy group. Because of this fifth homotopy group for SUN and the SPN, you can get a discrete theta parameter in 60. In this case, discrete theta parameter theta equal to 0 and phi. So this theory will be 60 theory. This SUN theory. And the SPN theory, we can have discrete theta 0 and pi. We call this to be C and C prime 0 and pi. Now, so why is they are called the little string theory? They are now quantum field theory. Quantum field theory means we have a locally well-defined energy momentum tensor, and we have a clear sense of localities. But this 1,1 little string theory and the 2,0 little string theory, they are related by T-duality, which means winding mode. Once we compactify on a circle, winding mode and KK momentum, Klein both are exchanged. So that, remember, Klein mode is about locality along the compact circle. But once you change the winding mode, then locality is lost. So AD case, so either 2,0 or 1,1 on circle R and the dual circle R tilde. And then, for example, KK momentum here will be 1 over R. Will be winding mode along this direction. So R tilde over string. And the winding model in this direction, so I have fundamental string wrapping the circle whose energy is like that, that will become KK momentum. And this is allowed if, okay? So if we, without twisting, we start with AD type of 2,0 theory, or Yang-Mills theory is 1,1 theory, circle compactify with relation between radius to be like that, then you get the same 5D physics. Where winding and the KK momentum are exchanged. In addition, in 2,0 theory, I said that little string theory, little string or fundamental string is fractionalized to, so here, suppose I don't wind the string, I just have a little string outside without wrapping it. Then 2,0 theory always is split into 2,0 theory, non-winding mode is split into self-dual string with constant number h. So those are like pattern, number of patterns. It's split. But 1,1 theory, usually instanton, you cannot split. Instanton quantized, and you cannot split it as an object. But once you circle compactify, you can turn on the gauge holonomy. Turn on the gauge holonomy, which breaks gauge symmetry to U1 subgroups. then instanton split into magnetic monopole, or 6D to 5D case instanton string split into magnetic monopole string. And similarly, self-dual string, which is not wrapping the circle, becomes a monopole string. So both cases, even though before circle complexifying, this non-winding string is not split. Once you get total holonomy, which is like a super selection sectors, then they split and they get the same physics for non-winding little strings. So thread is like a big thread split into number of the components, which is, and each one of them is charged strongly. But you can split them because they are PPS object and there's no force between them. Right. So again, so we study 70, then circle compactify, and then we do twisting, and then we get these non-split groups. But you would ask, how do you get theta terms? And turns out there's a little more subtleties because when you model out, this is possible only for A type of theory. So A type is C2 divided by Gn. And then if n is not a prime number, say 2 times 5 or 3 times 5, then I can circle compactify. During that process, you can do G3 modding. So that reduced the 15 to 3, to 5, and then this non-trivial theta term appears. And the little string theory turns out to be possible only for theta over 2 pi being rational number, which is argued by Witten. So if they are non-rational, then you cannot take up the gravity. So little string theory is possible for rational theta parameters. So you can see it's very rich. So 1,1 theory comes with all kind, little string theory comes with all kind of variety. Other than the 2,0 theory is very simple and only AD type. But T-duality should generate all of that back and forth. So that was one of the main questions we had, and also Michela Del Zotto and Lakshya, they worked out a certain aspect of it. Right. Yeah. Yeah. No. So turns out, suppose I study SU 15 and 70, then I do model out circle compactification, and then I do use one of G3, then I end up with SU 5. And depending on how you do G3, theta parameter becomes theta over 2 pi times 3 about which I'll tell you more detail. How you get, so you reduce the rank because of locking between them, and then you reduce the rank under the theta parameter get generated. Oh yeah, so you fix this one, but instead of 3 times 5, you say 3 times million or something. That's like it. Right. So twisting is related to symmetry of the thinking diagrams in twist affine case. So we have A type and the D type. So there's a symmetry, then we can do twisting using this one, G2, 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 and G2 and G3. Okay, so we use those symmetry of thinking diagram to twist the theory to low dimensions in K theory case. Or also even two-comma theory case, we can twist the two-comma theory. And conformal field theory case, there's no affine node. And this case, again, we can twist it. And in that case, one gets something interesting. For example, there's A2R minus 1. One, two, three, four, 5. Then we do twisting this G2 symmetry. So, for example, A5, 2,0 SCFTs, and then G2 twisting, then we get a I'm confused. Right, so because alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, and beta 1 is alpha 1 plus alpha 5, and the beta 2 is alpha 2 plus alpha 3, and beta 3 is equal to alpha 3, so it becomes a short. And then on the twister, we get say, SO7. So if we start with 60, two-comma conformal field theory of A5 type and circumconvex by twisted, then we get SO7, which is 7 by 7. So it's not Yang-Mills theory. If it's 6 by 6, then it got bigger, 7 by 7. And because it's not Yang-Mills theory, you can get this theory. That's how you do twisting of two-comma theories, conformal field theories. But if I think about two-comma little string theory, then we have affine node. So we have affine node, and then we have affine node for, and then for example, E8, T4. And then even though those are not K theories, as we did the twisting of conformal field theory, two-comma conformal field theory, we can twist these theories. And there are more symmetries. So these are obviously G2 symmetries. And then you have a GS symmetries, because I can rotate this node. And also this one has G2 cross G2 symmetries. I can identify like this. Maybe there are a bit more. And this one is a G3 symmetries, G2 and G3 symmetries. And this one is G2, G3, and G4 symmetries. So two-comma little string theory allows a lot more twisting. That's why we have so rich 1,1 little string theories, because we can twist the two-comma little string theory using these nodes. Okay, so those are the symmetries of the affine thinking diagram. And usually, K theory, we don't use affine thinking diagram to twist it, even though I assume that if we study, say, Yang-Mills theory, which we go to, say, 6D Yang-Mills theory to 5D, then we have a twisting of Yang-Mills theory. But you can go to 4D. Then 5D theory is already affine. So probably when you go to 4D, twisting, one can do similar things, even without little string theory, because you double compact by once, then you get affine thinking diagram, then you can twist using this affine thinking diagram, and that will be more interesting way to, but I don't think people have studied that part of twisting. Did you? No? Yes? You're the expert. So if you do torus compactification, you can do more twisting than just a circle compactification. But I don't think people have explored that story much. Right. So that's the part of stories. And before I go further, wow, I thought I started 2:30. So we did partition function of the D theory, the class of partition function. We use modularity and we go to Cauchy limit, blah, blah, blah. And then we get the black hole entropies. You can think about the theory on two-combinatorial theory on torus times R4, and then you can think of a lot of momentum flowing with angular momentum along it. And then we found a rather interesting relation between these two cases and all the twisting case. So this case, for example, Cox number is 6 and dimension is 35. We divide by order of our automorphism, and that's 3 times 7 times 5 times 7. Now, this case, SO7, Cox number is 5 and dimension is 21, which is 3 times 7. So you can see they are the same. And the reason is that Cauchy limit means I'm looking at short distance physics, and twisting is about long distance physics, and the degrees of freedom doesn't change with the twisting. And that invariance is appeared as a preservation of degrees of freedom in two-combinatorial theory, where it's a product of the Cox-Coxman and dimensional group. So it turns out it works out for all the cases. Right. So we want to show the T-dual between two-combinatorial AD type. And I said that the affine thinking diagram is more symmetries. So let me just show one cases. One can go over all the cases. So surface. So 1,1 theory with gauge group SO2R plus 1, and then we circle compactify because it's a non-split group, we cannot twist it. So we circle compactify, then we get this thinking diagrams. And this can be obtained by twisting of the D-type series. This type of G2 twisting generate this series. And basically, root of this guy is some of the identified ones. So this is a short root, and this is twice bigger. That's why you have these arrows. And so, and it's very simple. And one can go over all the cases, and one can discover all the origin of the two-combinatorial theory from this twisting. Similarly, also we can twist the 1,1 theory, A-type series. So we can do I think it's 0. And discrete zeta is 0. You can have discrete zeta equal to pi around the SP side. And this comes from D1 2R plus 3 divided by G2. And So here's one node which is not fixed, but here there's no node in between, and then same sort of things. And that's the theory you get. So even though two combinatorial theory, they look very similar, but once you do G2 twisting, corresponding 1,1 theory are rather different. So we want the testing of the T-duality, which means best way and simplest way is counting BP subject. So we calculate a partition function of the series. So we want to test by comparing the partition function. On our focus T2 with omega deformation. And each partition function is made of the perturbative part and the stringy part of the stories. So so both of them has a perturbative part and a stringy part. Now, two combinatorial theory, perturbative part is basically this partition function is counting mode which is moving with speed of light along the circle computation. And then which carries KK momentum plus various rotational angular momentums related to. So if I calculate, there are J1 and J2 related to 1, 2, and 3 for plane. And then transverse direction, there's R4 direction, and there's SO4 R symmetry, which is made of R, JR, and then additional parameter M. So roughly, there are 4 independent charges, but supercharge is preserved only under the combination of the JR plus J, this sum plus JR. So there are only 3 independent chemical potentials, and so those are called epsilon minus, epsilon plus, and M. So roughly that gives us chemical potential for angular momentum along the 1, 2, 3, 4, and then transverse directions. So one can define the partition function for each 2, 0 theory and 1, theories. And you turn on the gauge holonomy for 1, Yang-Mills series, and 2, 0 theory strings strings are already fractionalized. On the other hand, the perturbative part of the 2, 0 series is rather simple. It's just a plastic exponent of some component I minus. So Q counts the KK momentum along the roughly along the M circles, and the rank is R, then this quantity, and the I minus is just function of M and the epsilon minus and the epsilon 1 and epsilon 2. I'll not write down the total form. And string part is made of the string partition function, and each string is given in terms of the self-real string number at each affine node, which is given in terms of k vectors. So k0, kr, alpha 0, alpha r, that will be the string charge, and then fit the so tau is again q equals to e to the 2 pi I tau, measures the kk momentum, and p is e to the 2 pi I rho, measures the winding And then it's fractionalized, so depending on charge and how much tensor branch it has, there's some weight. So that's a rough picture of this 2,0 partition function on T2 cross R4. Now, 1,1 theory, you compactify on areas, and then KK momentum is now winding mode in this side, it becomes KK momentum in this side, so it becomes the perturbative part of it. So this part is roughly given in terms of right. So it's and then there's Cartan part and then positive root. And then negative root has to have KK momentum. That's perturbative part of a partition function. Now, string part is very simple because it's just the instanton string. So this will be just and then this will be P omega. There's also omega or rho omega, and then epsilon plus minus. And so roughly this counts the instanton string, this counts the fractionalized strings. Now, SVN case, both answers are known exactly in terms of Young diagram. So SVN case, both cases known, and one can calculate really hard and compare two partition functions, generate the identical answer. Now, challenge is D and E case, also non-simplest group, and there are a lot of additional subtleties. For example, instanton string in 1,1 theory with non-simplest group is not little string. It's fractional little string. Maybe you heard the instanton in SPN theory has half instanton numbers or something. So it's q to the n divided by fraction. So when you wrap the instanton string once along the circle, dual circle, you are not creating the full KK momentum from 2,0 side, you get a fractional part of it. And also, when you compactify 1,1 theory on a circle with a twisting, you generate a fractional KK momentum. So you end up here, this side again, you end up some fractional part on the KK momentum string part of it. So there are a lot of such things going on, and we have solved out that pretty much completely. And also, SU and theta turns out that low energy effective Lagrangian is so suppose I have a bare coupling constant. Then we do with D1 plus D5 rings, then we make a transformation using that, then we end up with a new coupling constant, which is A over C plus I G0 over C squared. And then we end up with A D5 plus C NS5. And then we end up with G0 going to infinity, which is equal to the coupling limit of new string constant, and that's how you decouple the gravity. On the other hand, the low energy physics doesn't change, so you still use all the theta parameters, and And then one can see, for example, if I have a CT1 string and the minus D fundamental string on D brane is just electric charge, then you transform this, then this ends up with minus 1, 0, which is fundamental string. So fundamental string is made of the CT1 string. So little string is made of C number of the instanton string. So that's why instanton string carries tension, which is 1 over C of the string tension. And that's the effective Lagrangian you get. And so in this case, again, fractional value is 1 over, this fractional part is, which you use is FC. So one can go back and forth between perturbative paths and stringy paths, then you can calculate and show T-duality holes. So let me give you a little more specific example. And then close that the sessions. So Gn so this is a weight zero modular form with index I and Z. So if I have modular transformation, so E and G are the same thing. And then turns out this is true for when you have this fractional KK momentum, you can have A, B, C, D belongs to not the SL2G, belongs to gamma 0 and F congruent subgroups. And then this index of the modular form is given in terms of anomaly inflow. For two modular theories, one can work out for same thing for 1, which is simpler. So one can calculate that as a function of the epsilon plus minus and m. So you can, it's a function of k charge and the epsilon plus minus and the mass deformation parameter m. And then using that, you can restrict this elliptic genus or stringy partition function very precisely. So, and then there are additional tools we have for partition functions. So all the ADHM technology for classical group works, and also G2, maybe you guys have heard of use. ADHM has been found about 5 to 10 years ago. So G2, one can have ADHM technology using the G2, SU3 is a part of the G2. So you do ADHM on SU3, but then there's an alternate method of the G2, which belongs to fundamental representation of SU3. And then you use ghosts like fermionic contribution, which captures that physics by reducing the supergeometry. And this is all done by Kim and his collaborators. And then one can write down the partition function for G2 case. And so one can do that. Or you can have blow formulas with some sort of recursion relation on partition functions. And third one is modular bootstrap. Has been also Telgiotto and Lockhart. They worked out also. If you have instant partition function, then you can have a numerator and denominator. Denominator some well-known, and the numerators, you know some modular properties. Then you use the generative function to write down general forms, and then you can have like 10,000 terms. And then using various T-duality and so on, then you fix the coefficient, and then you can, a lot of times you can fix the coefficient exactly. Then you get the partition function. Then you can test the T-duality further by comparing with the other side and so on. So using this technology, one can find, with a lot of work, find a smaller, lower level of the particle string case. You can do the partition function, then you can compare the T-duality. And of course, what else we expect it works. But it's more challenging from the technology side. Right, so let me conclude. So one of interesting part of the story is Cardi limit and black hole physics. So as I say, 2D and 6D two-comma super confined field series, one can do twisting, one can do Cardi, and the invariance of physics led to interesting identity between product of the zero Cox number and dimensional group. And I've been asking mathematicians and physicists for the last 3 years whether they have seen this, if they saw it where. And so far, none of them saw this one before, even though such a simple identity. And also, little string theory can have similar pictures because a little string has tensions. And if I look at the little string on a circle with a large KK momentum with a twisting, again, the story should be similar. We have ADS3 physics, and there is some ADS3 black holes, and the twisting generate different type of partition functions from little string perspective. So Cardi limit of those things haven't explored, so we are thinking about it. And then without testing, A-type theory is related to genus 2 modular forms, Siegel modular forms. So rho related to P and tau related to P, Q, and the M3 of them are this modular parameter for SL4G. And people work at a little bit of a cyber curve, but that was the end of the story. And I assume there are a lot more stories to be discovered. And also, of course, if you think about codimension 2 defect, integral models, PPS quivers, those are all stories that people haven't touched yet. So those are also interesting challenges. So let me close the session. Thank you.
Again, you just mentioned connection to Siegel modular forms.
Yeah.
Is there a favorite example of yours where you can interpret some of the tau and epsilons as parts of a higher genus theory of the matrix?
Right. So I think a rho, which is e to the p equal to e to the 2 pi I rho, and q is e to the 2 pi I tau, and the e to the 2 pi I m, maybe r. So those are Siegel modular form modular parameters. So I don't know much about this. Maybe you saw rho, tau, m for SL4G.
So would you know an example of a theory of a partition function which has a, well, hidden genus 2 modularity?
Right, so I assume that I haven't tried yet. Even though you can expand the string part of each one of it, you can write a closed form in terms of a generating function of the Siegel modular forms or Siegel Jacobi forms. where epsilon plus minus are sort of J parameters, but I don't think anybody tried, and that's my fond goal and ambition. Master the Ziegler model forms, then write down the answer in simple form instead of going around the bushes. But people have wrote down cyber-Eaton curve in terms of Ziegler model forms. Yes. Even 1,0 certain class of theory is very natural. So for example, if I think about so M circle with NS5 brains and multiple T6 brains, T6 brains with NS5 brains, and then there is natural duality between extending N and M, and so their Ziegler model form seems to be very natural place to play. Kind of.
Sorry, were you saying that?
That's a 1,1 leader string theory. 1,0 leader string theory. So there, remember 2,0 case, fundamental string is fractionalized, but 1,1 is not fractionalized. But this case, they are in equal footing because it's a 1,0. And there are more symmetries, and that's the natural place where one can expect the Ziegler model form appears more naturally.
So are you saying that some of the duality moves in this
Yeah.
physics setting corresponds to the generators of SP4?
I think so. But I'm just aware of the direction. I haven't really tried any concrete examples.
Who are the authors that one could consult on this?
Right, so there's a long time ago, 15 years ago, there's, of course, Kunran Papa, but his collaborators, I explain my, because when you don't see the name often, then you gradually your name disappears. I know his geographic locations, but right. And then there's a Babak and Ruizan. They wrote on cyber-Eaton curve about 5 or 6 years ago. Babak Hega.
Sorry, you were mentioning Asian construction for G2.
Right.
So one can in principle compute the castle
It's done.
with arbitrary magnetic formation.
Yeah.
For G2.
Yeah. But usually user arrives late in some corner of universe. It is well known by Sok and his collaborators.
So even for, well, I'm biased. I'm interested in equal to stuff.
I'm sure that's also can be true. Yeah.
More questions? Then if not, we can thank you for that.
All right, thank you.